Hello, everybody. My name's Jacob Maag, and today I'm going to be running through my master's project, which was titled Elucidating Quaternary High Frequency Depositional Sequences and Incised Valley Evolution using High Resolution 3D Seismic Data in the Gulf of Mexico, USA. So I'll start out with the motivation of this project, which is that there are limited seismic analyses on late quaternary high frequency sea level cycles and the subsequent evolution of small scale fluvial systems on the Gulf of Mexico's inner shelf. So when I say high frequency sea level cycles, we have first through fifth order cycles. I'm talking about fourth and fifth order cycles specifically. When I say small scale fluvial systems, I am referring to the Brazos and Trinity rivers specifically. There's limited seismic analyses on such features because conventional 3D data is unsuitable for these types of studies. However, we have some high resolution 3D seismic data in the Gulf of Mexico, and we are wondering, can high resolution 3D seismic data be used to gain an understanding of late quaternary high frequency sea level cycles and channel evolution in the northern Gulf of Mexico? So, like I said, our study area is the northern Gulf of Mexico, and the age of the deposits that we're going to be looking at are quaternary. So, here is a geologic map of the North American continent and the Gulf of Mexico during the quaternary period. And we can see our study area is in this red box specifically, and it lies just near the Brazos and Trinity river outlets. You can see those rivers are right here. And we know that over the past 400,000 years, there has been a lot of glacial activity, a lot of interglacial periods as well. And as a result, sea level has fluctuated by more than 130 meters. This has given us 5 high stand events, as you see up here, and more importantly, 4 low stand events, which we see down here. So to orient everybody with the sea level curve, because I will be referring to it quite a bit throughout this talk, here is the last glacial maximum. So this is just 20,000 years ago. We are currently up here at present. And then if you go prior to the last glacial maximum, we had another low stand event. Prior to that, we had another low stand event. Prior to that, we had another low stand event. These low stand events are called the marine isotope stage, or MIS2, right here. And then the MIS6 right here, the MIS8 right here, and the MIS10 right here. So as you can imagine, currently our study area only lies in about 14 meters of water. So if we have been changing sea level by over 130 meters over the last 400,000 years, our study area has been subject to many subaqueous and, more importantly, subaerial conditions. So within our study area, this is the first seismic inline I'm going to show. We have many characteristic features of the northern Gulf of Mexico. So most importantly, up top here in our shallowest, about 200 milliseconds, we have a bunch of unconformities. And then the elephant in the room is over here in the northeastern portion. We have this big salt diap here. And then, of course, we have a bunch of normal faults over here in the southwest portion, by which we also have a pretty large gas chimney here. This gas chimney does cause some distortion in the data, particularly in the lowermost portion of the interval of interest, and I will show you kind of the effects of that here in a little bit. But for now, I want to talk about these unconformities up here and why they are important. So we know that unconformities represent times at which the continental shelf was subaerially exposed, which would be during eustatic low stand events. So like that MIS2, MIS6, and MIS8 and MIS10 low stands that I just showed you. So in theory, each unconformity within the study area should correspond to a time of decreased sea level on our sea level curve. As a result, we would expect these unconformities to be forming here when sea level is low. We should be able to correlate them to the sea level curve. What this does for us is provides sort of a constraint for a sequence stratigraphic model, which we will be building here shortly. For now, though, let's talk about the data that we have. So This study did rely solely upon a high resolution, high frequency 3D seismic survey located just south of San Luis Pass, Texas, right here, as indicated by this red polygon. It's about 16 kilometers offshore. The survey was acquired in 2013 by Tip Meckel and his colleagues down at the University of Texas. It's a small survey. It only covers less than 30 square kilometers, but what makes it so unique and so great is its small bin size of 6¼ by 6¼ meters, and then most importantly, its very high dominant frequency of 130 hertz. The sample interval is rather small. It's half a millisecond, and then the record length, because this is a high frequency survey, high frequency waves are easily attenuated, therefore not able to penetrate very deep. So it is a pretty shallow survey. It only spans about 1600 milliseconds deep. However, that does not pose any issues for us because we're interested in the shallowest subsurface, only about the first 200 milliseconds. So because we're working so shallow, there is no well data through the interval of interest, because that time of 200 milliseconds basically is a depth of roughly 125 meters. We're interested anywhere from the seafloor at 0 meters all the way down to about 125 meters, but too shallow for any well data, so logs or core. However, the survey does give us a very great resolution, vertical resolution of 2.9 meters, and then we have a lateral resolution of just under 6.5 meters. So what this looks like versus conventional seismic data is something like this. So over here to the right, we have the typical thickness, or in this case time, of first through fifth order depositional sequences. And we can see our conventional seismic data here in this red and black color scale is very useful in delineating these first through third order, say, depositional sequences. It has the resolution to do so. However, when you get over here to these fourth and fifth order depositional sequences, these higher frequency depositional sequences, we can see that this conventional seismic data will struggle to really detect or more specifically resolve these depositional sequences. While they might show up as a single peak or trough, or maybe a couple or three, there's not going to be as much detail within these sequences to actually do a sequence stratigraphic analysis. Something else you will notice here, like I said, we're working very shallow, so here's the seafloor up here. You can see here that the conventional seismic data is muted in the shallowest, about 500 milliseconds of the subsurface. So that does us no good either. However, we can see in the background here in this grayscale seismic data, that is our high resolution seismic data, and we can see that we have data all the way from the seafloor basically down to as deep as we need it for this study. And most importantly, the resolution is sufficient to look at these fourth and fifth order depositional sequences. Now, I don't want to spend too much time on this, but with this high frequency data does come a little bit of a downside, and that is that this survey does have a very strong acquisition footprint, and it is just inherently noisy. So at shallow depths, this is at a time slice from 30 milliseconds, we can see this very prominent northeast to southwest trending acquisition footprint here, all these lineations here. And what this looks like in cross section, so now we are running perpendicular to that acquisition footprint, is something like this. You can see we can see that acquisition footprint very well in cross section too. And then, like I said, this data is just inherently noisy, being that it is so high frequency. So to start with our workflow, the first thing that we did in step one was did some data conditioning, and then moved on to our mapping of our unconformities. In step two, we ran a bunch of attributes and extracted the values of those attributes along these unconformities, so surface attributes. And then step three, did some unsupervised machine learning, which I'm actually not going to be talking about in this presentation for the sake of time. And then step four, of course, and most importantly, going to be making our geologic interpretations. So first things first, we need to identify and map our unconformities. So we'll kind of be using Vail for this, as he's kind of the guy that put all this together in 1977. He defined an unconformity as a surface separating younger from older strata along which there is evidence of subaerial erosion, null truncation, or subaerial exposure. So using this logic, in the shallowest, about 200 milliseconds of our seismic survey, we identified 3 major unconformities. All of these unconformities, of course, are characterized by the lateral truncation of reflectors, as we can see here, indicated by these red arrows. And then, for simplicity, these unconformities from deepest to shallowest were named lower unconformity, or LUC, middle unconformity, or MUC, and then upper unconformity, or UUC. So we need to know the depth of our unconformities, and I'll get to why this is really important here in a little bit. But this is a little tricky because my data, or our data, is in the time domain, and we really need velocity to get an accurate depth. However, luckily in the 1990s, Exxon conducted a bunch of check shot surveys in the area, and they determined the average interval velocity down to about 150 meters to be 1,525 meters per second. We also know that the sea floor lies at 19 milliseconds, and this is important because we want to know the depth of each unconformity in meters below sea floor. So we're using the sea floor as our datum. So, of course, we know the time at which our unconformities lie. So we can use this equation down here to derive the depth. And of course, it is important to keep in mind that these depths are approximate. So we find that our upper unconformity, our shallowest unconformity, lies at 17 meters below the seafloor. Our middle unconformity lies at 60 meters below the seafloor. And our lower unconformity lies at 112 meters below the seafloor. And I'll get more into why this is important here in a little bit. For now, let's talk about the attributes that we computed. So you saw I'm mapping unconformities. So along these unconformities, I'm expecting to find fluvial features. So I computed attributes which are specifically known to enhance fluvial features. So starting out, like you saw, this data is pretty noisy. So I ran spectrally balanced amplitude just to clean that amplitude volume up a little bit. Next I ran sweetness, and then I start getting into some geometric attributes. So we ran Sobel filter, K1 or positive curvature, K2 or negative curvature, and then valley shape. So first I'll show you kind of the overarching features along each unconformity. And if you remember, I mapped all of these in detail, so I can very simply produce time structure maps. So that's what we see here, are time structure maps of each unconformity. And these are actually co-rendered with amplitude, just to kind of pull out some of those more subtle features. So down here we have our lower unconformity, or LUC. We have our middle unconformity right here, our MUC, and then up here, shallowest, we have our upper unconformity, or UUC. So just so everyone's clear, these are like mapped view images of each unconformity. And I want to go back down to our LUC and touch on this gas chimney here. I told you that it distorted the data, specifically in the lowermost portion of our interval of interest, and this is basically what it caused. So it basically disabled me from being able to map part of this lower unconformity, because like you saw and like I said, the data was very distorted and I could not confidently map through that area. So I avoided that area just on the lower unconformity because I didn't want to be inaccurate. But nonetheless, we can still see the main fluvial features along this lower unconformity. So we can see this main channel here, and then we see a bunch of tributaries, dendritic tributaries. And then, of course, we have a lot of structure down here, deeper. We have normal faults, And then we have this salt diapir over here that you saw earlier in that inline. We move up to the middle unconformity. We have this nice big meandering channel going through here, and then a bunch of dendritic tributaries and maybe some crevasse splays. And then still have our normal faults and our salt diapir, of course. And then finally up here in our upper unconformity, we just have this really large dendritic incision. And what you'll notice here is that all of these fluvial features are trending in the north to south direction. So when you look at spectrally balanced amplitude by itself, what you see is that this attribute is just really helping to reveal subtle tributaries along each unconformity, as indicated by these green arrows. However, interestingly, we also see these negative amplitude anomalies, specifically along the upper and then mostly the middle unconformity here, all these negative amplitude anomalies. Sweetness, being that it is partially derived from amplitude, we see a similar trend. So we just see that this sweetness attribute is further enhancing these subtle tributaries, and then now you can see, you can really see these amplitude anomalies along specifically the middle unconformity, as indicated by these red arrows. Okay, so now we get into some geometric attributes, and we're going to start with Sobel filter, which is a edge detecting attribute. And because of this acquisition footprint and because of the noise, geometric attributes did struggle a little bit, but after messing with the color bar and the opacity, I was able to get them looking presentable. So we can see here, like I said, it's an edge detecting attribute. So this Sobel filter is enhancing the channel and tributary margins along each unconformity, as indicated by green arrows. And then importantly, mostly along the lower unconformity, because that's where we have the most structure, we are really pulling out some of these more subtle normal faults. These yellow arrows are indicating normal faults, which I had previously overlooked in the original amplitude volume, but after running Sobel filter, really draws them out and makes them very clear. So the next attribute we ran was another geometric attribute, positive and negative curvature, which I have co-rendered here together and then with Sobel filter. And positive curvature is enhancing positively curved reflectors, such as levees and normal fault footwalls along each unconformity. And then negative curvature is really showing us negatively curved reflectors, which is important in these systems because that is going to highlight our Thalwegs for us. And then it is also going to highlight the normal fault hanging walls along each unconformity. Once again, we see this acquisition footprint pretty badly in this upper unconformity, being that this is a geometric attribute, but the attribute still performs as it should. The final attribute that we ran is valley shape, which is yet again another geometric attribute. And this is co-rendered with Sobel filter again. And we can see this one really enhances that acquisition footprint. However, it also really enhances channel Thalwegs, specifically along the upper and middle unconformities, as indicated by these green arrows. And then along the middle unconformity, where we have this nice meandering channel, we can see that this attribute is highlighting erosive scours on the outside of these meanders, shown by these yellow arrows. Okay, so I'm showing you all of these fluvial features along these unconformities, and there's a lot of just basic questions hanging out here, just simple things to be answered. So the first question being, which river system are these fluvial features related to? Well, I showed you how closely our study area lies to the modern day Brazos Delta, and it also lies very close to the Paleo-Brazos River Delta. So these features are likely related to the Brazos River. Now, that's not to say that it's impossible that the Trinity River contributed to the study area, but we're going to say that it is most likely, most plausible, that these channels are related to the Brazos River. Also important, we want to know in which direction was the paleo flow of these features. So I showed you all these features, all these fluvial systems are trending north to south, and we know that today river systems tend to flow north to south. So it is safe to assume that the flow direction along these unconformities was in the southern direction. And then finally, and most importantly, we want to know what exactly are these features. So I showed you that these features are existent along unconformities, which we know form during subaerial exposure of the continental shelf, which is the same process by which we know incised valleys form. So started doing some research and found that Dalrymple and Postman-Tier have actually written papers on incised valleys and their criteria, and found that these features along each unconformity do satisfy the requirements to be classified as incised valleys. They are regionally extensive, they are larger than a single channel, and they are accompanied by tributary valleys. Also important, Postman-Tier in his 2001 paper says that incised valleys on gently sloped shelves, like that of the Gulf of Mexico, often demonstrate a dendritic geometry. Now, that is not a requirement for incised valleys. Not all incised valleys are dendritic, but it's just one of those additional pieces of information that can be used as backing as to why I'm referring to these as incised valleys. Okay, so now we want to know, why do we care about these unconformities in the first place? Well, unconformities are very important in sequence stratigraphic analyses, which is what we're about to get into. So first, we should define a depositional sequence, which is a stratigraphic unit composed of a relatively conformable succession of genetically related strata, and here's the important part, bounded at its top and base by unconformities. So, in a way, unconformities, which are sequence boundaries, they act as sequence boundaries, are the general framework for a sequence stratigraphic model. Okay, so let me show you what that looks like in a little visual cartoon here. So we'll start with a sequence boundary, which likely formed by either non-deposition or erosion, or most likely a combination of both factors. And then we will have the deposition of an entire sequence. So one sequence is going to be composed of a low sand system tract, a transgressive systems tract, and a high sand system tract. So those three system tracts comprise one sequence. Sea level will then fall again, and we will have another sequence boundary form, on top of which we will have another sequence deposited, and then another sequence boundary, and then again, and it'll happen again and again and again. Okay, so what we can see here is that these sequence boundaries, as the name implies, they divide each sequence and kind of provide a framework. So if we can correlate these sequence boundaries in our study area, these unconformities, to low sand events on our sea level curve that we're using, we can then use our interpretation skills to fill in the rest of the model. So first we need to correlate these unconformities to eustatic low sand events. And like I said, we don't have any well data and we don't have any biostratigraphic data, so we're going to be relying upon previous studies, which is okay because the Gulf of Mexico is such a highly studied basin that there is a good amount of published literature on these types of things. So I want to remind you of the depths, the approximate depths of each unconformity. So our shallowest one is at 17 meters below the seafloor, our middle one is at 60 meters below the seafloor, and our lower one is at 112 meters below the seafloor. So I started first doing some research on the most recent low stand event, which was the MIS2 low stand. And I wanted to know if anybody has mapped the MIS2 unconformity regionally across the Gulf of Mexico. And in short, the answer was yes. So I specifically found these two publications from Sims and Anderson, whom mapped the MIS2 unconformity to be at depths of 16 meters here and then 20 meters here across our study area. So you can see our study area, our seismic volume is georeferenced on these maps, and one author found the MIS2 unconformity to lie at 16 meters below the seafloor, and the other one found it to lie at about 20 meters below the seafloor. So I showed you that our upper unconformity, our shallowest unconformity, lies at 17 meters below the seafloor, which closely matches those depths. So we can say that the UUC is likely equivalent to the MIS2 unconformity. In other words, what I have been referring to as the UUC is most likely the MIS2 unconformity. So moving on down, moving deeper here, started to investigate the MIS6 low stand, and I found that not as much detailed work has been done on the MIS6 unconformity. I did find one study about 40 kilometers to the northeast in Galveston Bay, which did map the MIS6 unconformity that we can see down here, and they mapped it to be at about 53 meters below the seafloor. My middle unconformity lies at 60 meters below the seafloor, which is, of course, a slightly greater depth than 53 meters. However, it's important to realize that this study that I'm using as a reference was conducted 40 kilometers to the northeast, so 40 kilometers up dip. So we would actually expect the unconformity to lie shallower in the subsurface up dip than it will in our study area. So we can say with reasonable confidence that the MUC is likely equivalent to the MIS6 unconformity. Finally, just moving on down the line here, I wanted to see, has anybody mapped the MIS8 unconformity? And the answer is no. The MIS8 unconformity has not been mapped in detail or really at all throughout the Gulf of Mexico. But slicing through the data and just using our geologic knowledge, we can say that the LUC, our lower unconformity, is likely equivalent to the MIS8 unconformity. It likely formed during the MIS8 low stand. So what this does for us is this basically provides the bones for our sequence stratigraphic model. So to recap what I just told you, we're saying that our lowermost unconformity formed here during the MIS8 low stand, our middle unconformity formed here during the MIS6 low stand, and then our upper unconformity formed here during our MIS2 low stand. So we can see over here that we kind of have the bones of our sequence stratigraphic model, and we have defined three sequences. So we have one sequence here, one sequence here, and then one sequence here. Now this uppermost sequence, we are only right here today, is likely incomplete, right? A lot's going to happen from here on. So it's important to keep in mind this uppermost sequence is likely incomplete. But nonetheless, we have three sequences we can work with, and when we apply our tripartite sequence stratigraphic analysis scheme, we get something that looks like this. So tripartite sequence stratigraphic analysis is simply dividing each depositional sequence into, as the name implies, three parts. So we're dividing it into the low sand system tract, the transgressive system tract, and the high sand system tract. And this is just done by identifying the bounding surfaces, which are our unconformities, which we already have identified, and then our transgressive and maximum flooding surfaces. So what is a transgressive surface? Well, the transgressive surface separates the low sand system tract from the transgressive system tract, and that simply represents the time at which accommodation exceeded sediment supply. Our maximum flooding surface, on the other hand, separates our transgressive system tract from the overlying high sand system tract, and that surface represents, as the name implies, the time at which sea level reached its maximum. So we can also correlate roughly those surfaces to a high stand event on our sea level curve. So what we see from this is that the low sand system tracts are mostly confined or entirely confined to our valleys. And then we also see that our transgressive system tracts are relatively thin. And that makes perfect sense because we can see that each low stand event was followed by a very brief and rapid period of transgression. So just not a lot of time for these transgressive deposits to accumulate. So I want to bring you back to the original question that we asked, and that is basically, can we investigate fourth and or fifth order depositional sequences with high frequency seismic data? So now we want to know, are these fourth or fifth order depositional sequences? And as we all know, 5 orders of sea level cyclicity exist based upon the following criteria laid out by Vail, Mitchum, and Goldhammer. And so on one end of the spectrum, you will have first order depositional or sea level cycles, which will occur over a very long period of time. So these are going to happen over a span of time anywhere from 200 to 400 million years. On the other end of the spectrum, you have fifth order sea level cycles, which will happen very rapidly. These are our high frequency cycles. They're happening every 10,000 to 200,000 years. And what we find is that these sequences, which we have outlined and investigated, do closely match the criteria of fifth order depositional sequences. So what does this mean what implications does this have? Well, commercially, hydrocarbon production is mostly focused upon reservoirs which were deposited within second and or third order depositional sequences. So here's where it is important to really understand the hierarchy and superimposition of these sequences and sea level cycles. So over a very long period of time, you will have a first order cycle as shown here by this red curve. This is going to happen, like I showed you, over any span of time from 200 to 400 million years. However, within that first order sea level cycle, you will have several second order sea level cycles, in which you will have many third order sea level cycles, in which you will have many fourth order sea level cycles, in which you will have many fifth order sea level cycles. So if you are exploring and developing second and third order depositional sequences, whether you know it or not, they might be below or they are below the resolution of conventional seismic, but you are dealing also with fifth order sequences. So the implications of this study is just that knowledge of these high frequency depositional sequences in the shallow subsurface may aid in understanding the small scale heterogeneity of deeper reservoirs where such features are unresolvable through conventional seismic methods. Okay, so part of understanding the heterogeneity is understanding how these sequences and their system tracks vary vertically and laterally. So valley evolution is going to play a role in that. Now, valley evolution undoubtedly occurred along each unconformity. However, it was best preserved along our MUC. And we can see here that when you slice down through the flattened data, so these are horizon slices, the system is showing us that it has a tendency to become increasingly sinuous and increasingly dendritic through time. So down here we're starting out with this very simple meandering system, and then through time it is becoming it's developing these very complex tributaries and crevasse plays. Now we want to know, why does this happen? Well, Pygott et al. 2011 did a study on the Gulf of Thailand, and they found that incised valleys in that area demonstrate a similar geomorphological phenomenon, of which they found to be in response to rapid transgression. I just showed you that each of our low stand events was followed by a period of rapid transgression. So this is likely what happened here. So to better explain this, here we have the sea level curve, and when we are in our low stand phase, we have these very robust fluvial systems trying to make it out into the basin, incising across the continental shelf. And then during the late low stand phase and transgressive system track, these fluvial systems basically become overpowered by rising sea level, causing them to flood beyond their banks and giving rise to the development of all these complex crevasse flays and dendritic tributaries. So, for my conclusions, we have several geological conclusions and then a geophysical conclusion. So, geologically, we found that yes, high resolution 3D seismic data can be used to gain an understanding of late quaternary high frequency sea level cycles and channel evolution in the northern Gulf of Mexico. I showed you that we identified and mapped 3 major unconformities in the shallowest 200 milliseconds of our seismic volume. I showed you that fluvial features along each unconformity satisfy the criteria of incised valleys, and they demonstrate a tendency to become increasingly dendritic through time, which is likely in response to rapid transgression. We correlated the LUC, MUC, and UUC to the MIS-8, MIS-6, and MIS-2 low stands, respectively. And then finally, the depositional sequences associated with each unconformity closely suit the criteria of fifth-order sequences. Geophysically, we only have one conclusion, but it's an important one. We found that the performance of seismic attributes was highly variable, as some attributes, specifically the geometric attributes like Sobel filter, curvature, and so on, were severely hindered by the volume strong acquisition footprint and low signal to noise ratio. So with that, I would like to acknowledge my advisor, Dr. Beadle, for her technical and financial assistance throughout this project and the final year of my master's, and of course the ASPE sponsors for their funding, and then all of the students and members. I'd also like to thank my other committee members, Dr. Pranter and Dr. George, and then all of my friends and colleagues from OU.